SEARLE'S vibration magnetometer. The aim of our experiment is to compare the magnetic moments of two bar magnets with the help of SEARLE'S vibration magnetometer. Here the apparatus provided is the SEARLE'S vibration magnetometer and a stopwatch for taking the time period of oscillation. The SEARLE'S vibration magnetometer, it consists of, as you can see, a small magnetic needle which is attached to a brass cylinder above a long aluminum pointer. The brass cylinder is suspended with the help of a torsionless silk fiber, and it is suspended and kept inside a glass jar as shown here. Now we are using this SEARLE'S vibration magnetometer to find the period of oscillation of a bar magnet. Similarly, the period of oscillation in the Earth's magnetic field. Now we come to the principle of SEARLE'S vibration magnetometer. When a magnetic needle is suspended in Earth's magnetic field and it is allowed to perform oscillations, the oscillations are simple harmonic. The period of oscillation T is given by 2 pi root of I1 by MBH, where I1 the moment of inertia of the magnet, M the magnetic moment, and BH the horizontal component of Earth's magnetic field. Now from this expression T, the frequency of oscillation N, which is equal to 1 by T, so we can see that the square of the frequency of oscillation N square is proportional to BH. That means as the value of BH or the strength of a magnetic field increases, the frequency of oscillation increases, or we can say the period of oscillation decreases. That is important. The period of oscillation is inversely proportional to the root of 1 by BH. Therefore, if the strength increases, the strength of the magnetic field increases, the period of oscillation decreases. Now, together with the Earth's magnetic field BH, if we are applying another field B1, usually this field is the field produced by a bar magnet on its axial line, and if the bar magnet is pointed towards the north direction, then the effective field is B1 plus BH. The field is get added up. Then we can write the frequency of oscillation in that particular case, N1 square is proportional to B1 plus BH, and from that we can write the relation N1 square by N1 square. Using the first two equations, we can write B1 plus BH by BH, that is equal to 1 plus B1 by BH, and from that B1 is equal to BH into N1 square minus N square by N square. Similarly, if we are changing the magnet to another one which produces a magnetic field of B2, a field strength of B2, the corresponding equation becomes B2 is equal to BH into N2 square minus N1 square divided by N square, where N2 is the frequency of oscillation in the combined field by the second magnet and Earth's magnetic field. Now using again, as we already mentioned, B is the magnetic field produced by a bar magnet on its axial line, and that is given by, here B1 is given by mu 0 by 4 pi 2 m1d divided by d square minus L1 square the whole square, and B2 is given by mu 0 by 4 pi 2 m2d divided by d square minus L2 square the whole square. And substituting B1 and B2 in the first equation or our third equation here, we are getting m1 by m2 is equal to n1 square minus n square divided by n2 square minus n square into d square minus L1 square divided by d square minus L2 square the whole square. So this is the formula that we are using to calculate the ratio of magnetic moments or the comparison of moments of two bar magnets. Here we are using the two bar magnets or we are placing the two bar magnets at the same distance d from the center of the SEARLE'S vibration magnetometer, and L1 and L2, 2L1 and 2L2 are the total length of the bar magnet 1 and the bar magnet 2. So this is the arrangement. The SEARLE'S vibration magnetometer is here. We are placing the bar magnet first in one side, and after that it is placing the other side, and the distance d is measured from the center of the SEARLE'S vibration magnetometer to the center of the bar magnet. Now we are placing the first magnet. Initially we want to find out the frequency of oscillation or the period of oscillation in the Earth's field. Then we want to find the frequency of oscillation in the combined field. So first we are having a tabular column to find the frequency of oscillation in the Earth's field alone. The magnet is placed. Now let us start with the experimental setup and the experimental arrangement. Now we are supposed to place the SEARLE'S vibration magnetometer along the magnetic meridian. Now for that we are supposed to draw the magnetic meridian on the table first. For that we can use a compass needle. As you know, the compass needle consists of a small magnetic needle and an aluminum pointer. Both are pivoted at the center and they are keeping always mutually perpendicular to each other. Now when we place the compass needle or compass box on the table, the magnetic needle aligns itself along the north-south direction and the aluminum pointer lies along the east-west direction. So we want to mark the north direction and the south direction. Now probably since the magnetic needle is very small, it is quite difficult to mark exactly the correct direction of north and south with the help of the magnetic needle. So it is better to draw the direction of the aluminum pointer lies, which gives the east to west direction. So we are marking the direction of the aluminum pointer, then removing the compass box, join the line, and that line gives the east west direction. Now this direction should be the east west direction. So this should be the east west direction. Now draw a perpendicular to this direction, the exact 90-degree perpendicular, and that direction gives the exact north-south direction. So we are having a north-south direction here. Now this should be the north-south direction. Now we can use the wooden board of the deflection magnetometer as a help. That wooden board is placed parallel to the north-south direction, that is parallel to the magnetic meridian, and the SEARLE'S vibration magnetometer is placed at the center of the wooden board. Make sure that the center of the SEARLE'S vibration magnetometer coincides with the center of the two lines drawn. Now the SEARLE'S vibration magnetometer is provided with a screw arrangement is there. With the help of that screw arrangement, we can move the magnet and the brass cylinder down and up. Now bring it down and then make the oscillations 0, that means it is not vibrating, no other disturbance are there. Then slowly rise and clamp it. Now the SEARLE'S vibration magnetometer is placed in the Earth's magnetic field. Try to avoid all other types of oscillations or disturbances producers, and the magnetic needle is performing a simple harmonic motion. Now in order to start with, we can bring a small magnet near to this one, that is just to oscillate, just to produce an oscillations. Don't take readings when you are bringing the magnet. At the time when you are bringing the magnet, leave some time for the so that it is performing perfect simple harmonic oscillations. Now we want to find out the time for 10 oscillations. One oscillation means the needle or the pointer is coming to one side, going to the other side, then it is coming back to the same side, then we are saying it is completing one oscillations. So let us find out the time period for 10 oscillations. We are ready with a stopwatch here. Now when the needle comes to one end, I will start. Next time I will started. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Now it is completed 10 oscillations. Here I got a time of say 17 seconds for the oscillations. Now we can repeat this one. That means the oscillations in the earth field 2 or 3 times. You can continue with that or bring the magnet again, allow it to oscillate, leave some time. Then you take the readings again, repeat it for 2 or 3 times. Then you find the mean period of oscillation for 10 oscillations. Then that value divided by 10 gives the period of oscillation, that is the time for 1 oscillations. Now we want to take the reading in the combined field. Now for that we are bringing the magnet. The magnet is brought. Now the magnet is having a north pole and south pole. Remember, the north pole should point towards the north. So initially I am placing the bar magnet at a distance of say 12 centimeter. At a distance of 12 centimeter, the distance is measured from the center of the SEARLE'S vibration magnetometer to the center of the magnet, and the magnet is placed north pole pointing north. Now this magnet is producing a magnetic field B1 at the center of the SEARLE'S vibration magnetometer, which is on the axial line. Now these two fields B1 and BH are get added up, so the strength of the field increased. As the field strength increases, the period of oscillation you can see it is going to decrease. When the field strength increases, that means in the combined field the period of oscillation decreases. So here again, as in the earlier case, we are finding the time period of oscillation. So let us find one time period of oscillation. Now we are going to start. Started 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now it is completed 10 oscillations. I got a time period of 6 seconds for 10 oscillations. Now this particular magnet is brought to the other side with the same north pole pointing towards the north and placed at the same distance 12 centimeter. The center of the magnet is at a distance of 12 centimeter from the SEARLE'S vibration magnetometer. Again we are finding the time. Once again we can find the time. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. So okay, almost we are getting the same time, 7 seconds here. So two times means keeping the magnet on the south side, similarly keeping the magnet on the north side, we determined the period of oscillation. Now it is repeated for the other distances. That means instead of 12 centimeter we are keeping at 13 centimeter, 14 centimeter, say 15 centimeter, 16 centimeter and 17 centimeter and 18 centimeter, both north side and similarly the south side. So as we are moving away from it, what happens that the strength of the field decreases and therefore the time period of oscillation is found to increase. The period of oscillation increases. Now these are the readings for the first magnet. Now remove the first magnet and bring and use the second magnet. Now we are having the second magnet, that is a magnet with less value of maybe magnetic moment, that is having a north pole and south pole. As in the earlier case, this magnet is also placed at the same distance, initially 12 centimeter in the southern side. Find the period of oscillation, then keep it on the other side 12 centimeter, again find the period of oscillation. Repeat for the second magnet also for the same distances, 12 centimeter, 13 centimeter, 14, 15, 16, 17, 18 centimeters, as we are done in the case of the first magnet. So that is the way we are taking the readings in the case of a SEARLE'S vibration magnetometer. Now we will see how how we will fill the tabular column. First case, we find the frequency of oscillation in the Earth's field. For that, we determined the time period for 10 oscillations. The SEARLE'S vibration magnetometer alone, initially I got a reading of 18, then again when it is repeated I got a reading of 18. Now I repeated 3 times. The third time I got a reading of 19. Then we have got the mean reading, say 18.33. Then the period t, that is equal to t by 10, that is equal to 1.833. Now from that we can find the frequency, that is 1 by t, and that is equal to 0.5455. So 0.5455. So that is observation in the Earth's field. Then we are coming to the first magnet and second magnet. The length of the two magnets are noted. The first magnet is having a length of 7.5 centimeter and the second magnet is having a length of 5.2 centimeter. Then we are using the first magnet first. The first magnet is placed at a distance of say 12 centimeter. Then we obtain the time period of oscillations as say 7 first. When it is placed on the other side, we obtain the time period as 8, then mean time period 7.5. Then we calculated n1, the frequency. First we calculated the period, that is 7.5 divided by 10, that is 0.75. Then the frequency is 1 by 0.75, say that is equal to 1.53, the frequency of oscillation. Now for the same distance 12, the second magnet is used. Then I got the time period of oscillation on the one side 10. When it is placed on the other side again, I got 10. Then mean is 10. Then the frequency we obtained 1. Now we can come, one set of reading is completed. Now you can find the value of m1 by m2 using our earlier equations. We obtain the value of n, n1, n2 and the value of d. Similarly, the value of L1 and L2 are there. So these are the values we required. L1, L2, N, N1 and N2. Then we can calculate the ratio of magnetic moments and we obtain a value of say 1.88. Now we are repeating the experiment, say for another distance, say distance 14 centimeter. Now for that distance, for the first magnet, we are finding the value of the period of oscillation, then the frequency. Now we are using the second magnet for the same distance 14 centimeter. The period of oscillation for 10 oscillation is find out, then the frequency is calculated, then the ratio of magnetic moment is determined. So similarly we can repeat the experiment for a number of distances, say 12, 14, 16, say 17, 18, etc. And each time we are calculating the value of m1 by m2 and we are taking the mean value of that ratio of magnetic moments. Now let us have a sample set of reading the observations. First tabular column is the reading of time period of oscillation in the Earth's field. We obtain the time period as 19, 18 and 18 second. Mean t is calculated, period t is calculated and the frequency is calculated. Then the observations for first and second magnet. The first magnet is having a length 2L1, the second magnet is having a length 2L2, that is 5.2. So we can have the values of L1 and L2. Then when the first magnet is placed at a distance 12, my observations are, readings are 7, 8 and 7.5 second, that is the time for 10 oscillation. The frequency is calculated. Then for the second magnet, the readings are 10. The second reading is when it is placed on the other side. Then the mean is taken, frequency is calculated, m1 by m2 is determined. Similarly, it is repeated for another distance 14 centimeter. So these are the observations and we obtain the value of m1 by m2 as 1.86. Then for another distance 16 it is repeated, 18 it is repeated and for a distance of 20 also it is repeated, and each time we obtain the ratio of magnetic moments and we find out the mean value of m1 by m2 and we obtain it is 1.72. So the result of our experiment is the ratio of magnetic moments, that is equal to 1.72.